Hello and welcome to another EE140 video in preparation for our upcoming midterm 2. Last video we did an example on normal incidence and wave polarization. So in today's example we are going to do an identical problem. The only difference is the incident wave polarization. So hopefully by doing this problem in both type of polarization will give us a better understanding on what is going on with these types of problems or concepts. So let us begin. So once again we are given 159 megahertz for our frequency, and from that we could get our omega, which is going to be 2 pi f, with f being 159, so 2 pi times 159 times 10 to the 6, that gives us 9.99 times 10 to the 8, or we'll just make it simple again and set omega as 10 to the 9. Okay, and we are given, so the only difference from the last problem and in this one is in the last video we were given LHCP, while here we are given RHCP. Alright, so the wave is incident normally along the z direction, so let's draw our z direction, and again it's normal, use green. Alright, this is normal to the z direction, and coming from air, epsilon r equals 1 to something that to a medium that has epsilon r equals 4. Okay, so it's going from here to there, and what that tells us is that the wave is also propagating from left to right along the z direction. So that's k sub I. So we could write down over here that k sub I is equals to k naught z hat. Okay, and the way we get the figure for k naught is going to be w k equals c. Rearranging the terms, get k equals w over c, and that just comes out to 10 to the 9 divided by the speed of light, and you still get 3.30. So we've done this, also drew this. Now next piece of information is that we are given E naught of I at 0, 0 at the origin with 2 volts per meter along x direction, and that is when we draw our xy plane, because remember we're given 0, 0, so that's x, y. So we initially have an E naught of I with 2 volts per meter sitting along the x-axis. Right, now we know that it's polarized using RHCP. Alright, so what we do, first off, we write down the axis once again. We designate them one by one, so x being our thumb, and a quick reminder again, when determining the axis we always use the right hand. So this is right, this is our pointing finger, again right hand, and z is going to be our right middle finger. So applying Z into the XY plane and using our right hand to figure out whether it's going in or out of the page, we determine that Z, positive Z, is going into the page, negative Z is going out of the page. So that information is useful until later too. Okay, so if this is our initial position, let that be our T equals 0, T equals 0, right? And knowing that case of I, or direction of propagation, is right along the positive Z axis. So applying this in this plane, that means it's coming out of the page. Case of I, or I'm sorry, that is also coming into the page right along the positive Z axis, right? So with those information and the fact that this is right hand circular polarization, we stick our right finger or right thumb into the page, right? Line our fingers along the x-axis and then curl our fingers. So if we've done it correctly, it's with right hand and our thumbs into the page, it should be curling this way. And this is our T is greater than 0. So again, from here, going here. And that is what this information is telling us. Okay. So from there, what we can determine is the second position, the second term for our E's of I, or E incident. Okay, so this is by right hand circular polarization. So we have the K, we have W, and we have epsilon R. So I think we're ready to write down our E's of I. So with that as our template, we write down E1s of I, the direction. So originally resting along the x-axis, along the x direction. So our E1 of I has an x hat, that's for direction. Now magnitude, we know we are given with 2 volts per meter, so that's 2. Phase, again, when t is equals to 0, the whole function is non-zero, so that tells you that we have a cosine. And we just put our omega 10 to the 9 t. Now our k is positive 3.33, so this means that this is going to be negative 3.33 along the z direction. Alright, now E2 of I, what is the direction? So let's look at this one. Initially it started from the x-axis and it's moving clockwise. It's heading to the positive, or it's moving towards the positive y direction. So over here, okay, we just put y hat, okay, the magnitude, which is 2 volts per meter. Now cosine here, so that means 90 degrees out of phase is going to be sine. And then our omega again, minus 3.33 minus k. Volts per meter. Now we just need to combine these two again to form, remember we are tasked to find incident, E sub I, reflected E sub r wave expression. So we just combine these two, combine it to form our E sub I or E incident wave expression. E sub I, it's gonna be x coming from here, magnitude cosine is a minus 3.33. Z, just remember it's along x or along z axis, k that is, then plus y hat 2, and then sine omega again, omega t minus k, just over here. That is along the z-axis. Finally, our unit, which is volts per meter. Finished writing the wave expression for E sub I. We are now moving on to writing the wave expression for E sub r. Now, how do we do that? Remember, we are given epsilon r 1, epsilon r equals 4. So from that we could write down our n, and n is our index of refraction, and that is just equals to root E sub or epsilon r. And again, quick reminder, this is only applicable to non-magnetic materials. Alright. So now that we know n, we could use it as n1 equals root of epsilon r for air, which is just 1, and n2 we could use that as epsilon r of the second medium, E or epsilon r of 4, so that's just going to be root 4, and from these two we could obtain our gamma, which is gamma is our fraction of reflection, that is equals to n1 minus n2 divided by n1 plus n2. Substituting root 1 minus root 4 over root 1 plus root 4. Okay, and that just leaves us with negative 1/3, which is also gamma. This gamma over here is equals to this one, right? It's also equal to this relationship, E naught or E naughts of r over E naughts of I. And why is this important? We are going to use E naughts of r to figure out the magnitude of our E sub r or E reflected. Since we are given E naught of I, remember we are given 2 volts per meter over here. We don't have E naught of r, but we are going to use this relationship or this ratio to figure that one out. So E naught of r is just equals to negative 1/3 times 2, that's from E naught of I, and that just gives us negative 2/3. We have the magnitude for our e's of r wave expression. So at least now we have magnitude. Now we just have to figure out the direction, phase, and unit. Okay. So for the direction of e's of r, or E reflected, we are just gonna copy the direction from e's of I. Alright, we are just gonna copy it. So over here, e's of r equals direction, copy the direction of the first term of e's of I, that is just x hat, and then multiply it by the magnitude, that is -2/3. Then write down our phase, it's still the same, cosine 10 to the 9 for our omega t. Now the question is, what about our k? So let's put a pause on that real quick and figure out k. Now from the first part, we know that ki is traversing along positive z direction. So for e's of r, we know that kr is just the opposite way of k's of I. So let's write it down over here. K's of r, right, equals, so if case of I is this, which is k naught z hat, case of r is just going to be negative k naught z hat. Okay, so now that we know that, how about the values? Alright, so if you remember, we obtain a value of k 3.33, but here we wrote down negative 3.33. So we're going to apply the same logic here. So 3.33 negative of that times negative, so that's going to be positive 3.33. Okay, hope that was clear. So that's for the first term. Now the second term, again we copy the direction from e's of I, that's just going to be y hat positive times the magnitude -2/3, then this is going to be sine times 10 to the 9 for omega t plus 3.33 z. Okay, and we'll write down our unit. Now we'll let the sign of the magnitude dictate the final destination. So since this is -2/3, we apply that over here, so we just get negative x hat times 2/3 cosine 10 to the 9 t plus 3.33 z. Then same thing here, we let the sign of the magnitude dictate the final direction, so that's just going to be negative y, negative times positive 2/3 sine omega t plus k there we go. Now we have our wave expression. Now, are we done? Almost. We just need to answer this final question. What is the polarization state of the reflected wave? What is this? Is this RHCP or LHCP? So let's draw it over here. Let's draw it big. We have our positive x, positive y, negative x, negative y. And it's also useful to copy this. So remember, we have an x, y plane. So x, y. Let's copy this. Let's copy the bearings of z on xy plane. So we know in xy plane, z is into the page and negative z is out of the page. We need to apply k. So we use blue. Okay. So we know that k propagates along the negative z direction. So we write down k sub r is also, since negative z is coming out of the page, k sub r is coming out of the page. Okay. Next, we look at this term, right, and this term. So what does that tell us? Well, that tells us that initially E sub r, or E reflective, or reflected, is resting along the negative x direction. So that is our t equals 0. That is, from here, from the first direction. So that's negative x, negative x. Now looking at the second term, negative y, that tells you that it's moving this way towards negative y. And if that is the case, then this one, sorry about that, this is our t greater than 0. Okay. So now that we have that, we just need what describes that transition from negative x to negative y. Is it RHCP or is it LHCP? And again, last video we asked the same question towards the end, and I said we just have to pick and try it out. Let me pick RHCP right now and see if that fits this transition or the description of this transition over here. So we know that k sub r is coming out of the page, so I'm trying out RHCP, right? So let me line up, or let me stick my right thumb out of the page as such, and then let me rest my fingers along the negative x-axis over here, because that's where initially we're going to start. And if I curl my finger using the right hand, right, I find out it curls this way, which is obviously not the trajectory or the movement that we need, because we need it to go this way. So once again, I'm wrong. But the good thing is we found out that it's not right hand circular polarization, which is in fact, it is left hand circular polarization, because if we use our left hand, stick our thumb out of the page, line our fingers over here, negative x-axis, and then curl our fingers, it fits the profile perfectly. Our fingers curl this way, and that is pretty much what we're trying to do. So in conclusion, Alright, we could write down, since it's asking us what is the state of reflected wave, E sub r, right, is equals to left hand circular polarization state. There you go. And we are all done. And just to compare, I don't know if you've seen the last video, but it's identical. Like I said, it's almost the exact same thing, except for that one we got started with left hand circular polarization for ease of I, which is this one, this wave that we got here. And we ended up with, last video, we ended up with RHCP for E sub r. Now, just comparing that with our video today, we got started with RHCP for E sub I, and we ended up with LHCP for E sub r. So you could draw your own conclusion, but what I was just hoping to point out is the similarities and differences in determining polarization of wave. I hope this video was clear and helped you out. Thank you for watching and have a great day.